Right. Good morning, folks. We are going to jump right into our 13.2 section today. So again, you should have access to that on Canvas. And I'm going to go ahead and start sharing my screen so we can take a look at that section. All right. So 13.2 is really an extension of what we reviewed yesterday. So yesterday we talked about parametric curves and how we could define those, how we could look at a set of parametric equations and kind of guess what shape it's going to be. And we also talked about the fact that there are multiple ways to represent any rectangular function with parametric equations, but we can do them. We might need to be creative depending on what our specific application is, but that was more just to get us thinking about the fact that there are so many ways of doing it, not necessarily that we need to make those decisions now. So we're going to start off today. We're going to cover two different types of applications of parametric equations. So the first application is going to be taking it all the way back to derivatives and taking a look at tangent lines and normal lines and slope, really. How do we find slope using parametric equations, since we already know how to do it with rectangular equations? And then in the second part of class, we're going to take a look at arc length. So how do we take a look at a parametric curve and then determine how long a particular section of it is, okay? So let's take a look with this diagram right here, okay? So right here, I have a diagram of a parabola. In fact, this parabola has the following equation. Y equals 1/4 x squared minus 1. And then I graphed it from -2 to 4. So if I'm graphing it from -2 to 4 of the x-axis, that means that I don't want the whole picture that's here. I really just want a certain chunk of that. So I'm really looking at from -2 all the way to 4. So I'm just looking at that particular section of it, okay? Now, if I said, hey, I'd like you to find the slope of the tangent line to any point of this rectangular equation, what I'd really be saying is find the derivative of this equation, okay? So when we're looking for the slope of any tangent line, that means we're looking for the derivative, okay? Now, we all know how to find the derivative of y equals 1/4 x squared minus 1. We would say that our y becomes dy dx when we take our derivative. The derivative of 1/4 x squared is going to be 1/2 x. And then just as a friendly reminder, the derivative of -1 is going to be 0. And that's something that I think sometimes when we're taking derivatives, we forget, right? When we have a constant, especially if the number is like a larger number, we forget that when we take the derivative, it's going to be 0. But let's not forget that here. And so what we have is that our dy dx equals 1/2 x, or we could say this is x over 2, okay? So if I wanted to say find the slope at x equals -2, what would that slope be?
-1.
-1, how'd you get that?
You plug in -2 for the x.
Yeah, you just plug in whatever x value, right? And if I said find the slope at x equals 0, you plug in 0 for x. I say find the slope at 4, you plug in 4 for x, and you get 2, okay? So that's what we spent a lot of time learning in the first part of Calc 1. So now we're going to extend this idea to what happens if we have it in a parametric form instead, okay? So this parametric equation is, in fact, what we have over here as a rectangular. So it's the same curve, but it's just written in parametric form. Now, oddly enough, when we take the derivative of parametric curves, we actually have to find it using the same idea that at the end we want to find dy dx, okay? And in order to get to dy dx, what we're going to need to do is set up a fraction. When on the top, we're going to find dy dt. So we're going to find the derivative of just the y part of the parametric curve. And then on the bottom, we're going to find just the derivative of the x part of the parametric equation. Okay, so we're going to take the derivative of the y part and we're going to divide it by the derivative of the x part. It's not quotient rule. Okay, it's not quotient rule here. It's just how we take a derivative when it applies to parametric equation. And so if we go ahead and find that derivative of y gives us what?
2t?
Yeah, that gives us 2t. Good, because 2t and then the derivative of 1 is 0. What about the derivative of the x part?
2.
2, right? Because the derivative of 2t is going to be 2. And so when we look at this, we can say, all right, these 2's are going to reduce to 1. And so really, the derivative or the slope can be determined by t. Now, you might say, well, t is not equivalent to what we got on the other side, but it actually is, okay? If I go back into the x equation, x equals 2t, and I solve for t, I would divide both sides by 2. And what I'd find is that t actually equals x over 2. So when I found dy dx to be t, I was really finding dy dx to be x over 2, which is good because if it's the same curve, no matter what form it's in, rectangular or parametric, I should get the same equation for the slope, okay? So this is just kind of an overview of what we're going to be taking a look at today, okay? So we're going to practice finding some first derivatives, and we're also going to practice finding some second derivatives, all right? So first derivatives, second derivatives, looking at slopes of tangent lines, but specifically cases where they are either horizontal or vertical, okay?
Can I ask one quick question?
For sure, what's up?
When you're coming to that equation, because yesterday during the quiz, I was finding it a little bit challenging trying to find direction, especially when you have sideways parabolas. My brain just wants to read it from left to right, kind of a thing. So finding the direction on something like that, would you just use the regular t, x, y table?
Yeah, so I would take like the beginning t value. So for example, the starting t value is -1, and I'd plug -1 into both the x and the y. That would be my quote unquote starting point, right? So if I plug in -1, I'm gonna get -2, 0. So this is my starting point. And then if I think about where it ends up, let me think about plugging 2 in. And so when I plug in 2, I'm going to get 4, 3, which means this is where it finishes. So if I were drawing the parametric curve, I would draw like just the section between the pink point and the green point, and then I would have arrows going in that direction.
Okay.
I have a question about direction too.
Okay.
So, for example, on the quiz, there was one question that at first I misread, was number 2, and I was wondering, after I realized it was how I misread it, if something was actually all values less than 0, right? Like not starting at 0, but 0 is the biggest number it comes to, would we start where the graph was, like -5, -4, -3, -2? Or would we start at 0, but to me, it starts at a number way less than 0, not 0?
We should always be looking at our t from smallest to biggest. Or in other words, most negative to most positive.
Yes, but I'm still, so do we just go from like 0 to -1, -2? Or if it's like, for example, if 2 would have been values less than or equal to 0 instead of greater than or equal to 0, that's kind of where I'm trying to.
It doesn't matter. You're always going from the most negative to the most positive when you set up your t-table.
Okay.
Okay, so the most negative number, it gives you your first point. Okay?
Okay, that's what I thought.
Okay. All right, so let's take a look at example number 1 over here, okay? So we have a set of parametric equations where x equals t squared minus 3 and y equals 2t minus 1, and we're starting at -3 and we're going all the way to 4. So if we wanted to make a table, like the first point we would plot is what happens when we plug in -3, and then the last point that we plot would be what happens when we get to 4, okay? Now, one thing that might be confusing sometimes is that occasionally the graph goes in both directions. So it'll go out and then it'll come back. And so that you just show by putting arrows in both directions, okay? But in this particular case, the question is asking us to find the slope of the curve at t equals 2 using the parametric equation. And so we're going to go ahead and find dy dx. Okay, so the word slope here means I want to find dy dx. And I know that I can find that doing dy dt over dx dt. Okay, and so if we take a look at our equations here, the derivative of the y part is going to be 2. And the derivative of the x part is going to be 2t. And again, like my first example, I can reduce those, but I want to be really careful because the t is in the denominator, it's not in the numerator, so it's not going to simplify to the same thing I had above, but in fact, it's going to simplify to 1 over t. Okay. Once you have that general equation, all you need to do is take whatever value you're looking for and you're going to substitute that in everywhere you see a t. So 1 over t is the general form, but for this particular question, they're saying what's the slope at t equals 2, and your answer would be 1/2. Okay? All right. So part B says confirm the slope of the curve at t equals 2 by eliminating the parameter. Okay, so we're going to go back to yesterday where we learned how to eliminate the parameter. And we have an x and we have a y. Which equation might it be good to isolate our t in, x or y?
The y.
Yeah, the y one. I would agree with that because if I try and isolate it in the x equation, I'm going to have to take a square root and it just adds another layer that I don't really want to add, okay? So if I take the y equation and I solve for t, I'm going to get y plus 1 over 2 because I add the 1 and then I divide by 2. And so everywhere I see a t in the x equation, that's what I'm going to go ahead and plug in. And so when I do that, I get x equals y plus 1 over 2 squared minus 3. Okay. Now, if I were to think about taking a derivative here, I'd probably want to simplify this a little bit so that when I take my derivative, it becomes a little bit easier to do, okay? So let's go ahead and just expand this out. This is going to be x equals 1/4 times y squared plus 2y plus 1 minus 3. Okay. And I'm going to go ahead and find my derivative using implicit differentiation. Okay. So that means that I'm going to have my 1 over here. This is going to be 1/4 times 2y dy dx plus 2 dy dx. And then that 3 goes to 0 when I take my derivative. Okay. So let's make a little bit more space here. I'm not sure what I was trying to squeeze into this tiny little box. Oh no. Okay. All right. So if I distribute that 1/4, I'm going to get 1 equals 1/2 y dy dx plus 1/2 dy dx. And when I'm trying to find a derivative, I'm solving for dy dx. And so I like that on the right-hand side, it's a factor in common. And so I can factor out that dy dx, okay? And so that's going to give me 1 equals dy dx times 1/2 y plus 1/2. And I'm going to divide both sides by that 1/2 y plus 1/2. And so I'm going to get dy dx equals 1 over 1/2 y plus 1/2. And so if I want to find the slope at t equals 2, I can't just plug 2 into here because I don't have a t anymore. I only have a y. So how do I figure out which y to plug in here?
Plug 2 into your y equation at the top.
Yeah, we're actually going to take 2, which is the value we want to find it at. We're going to plug it into here. Wow. And see what y value corresponds with that t value. So when I plug in 2, I get 2 times 2, which is 4, minus 1 gives me 3. So everywhere I see a y in this equation, let's plug in 3 and see what happens. So dy dx equals 1 over 3/2 plus 1/2. Okay, well, these aren't bad as far as fractions go. 3/2 plus 1/2 is going to give me 4/2. 4/2 is the same as 2. So I end up with a slope of 1/2, which is good because that is equivalent to what I got finding it using parametric equation. Okay. So the purpose of showing these two side by side is because one of them took up significantly less space than the other, first of all, right? So we always want to go for the most efficient method that we can. And yes, we could, if we got stuck, we could convert it to rectangular and then take the derivative and then find the point that corresponds and then find the slope. Like that is a mathematically valid way of doing it. But I feel like we all are always looking for ways that are shorter or more efficient and have less room for mistakes. And so when I look at that first side, part A, I'm like, oh yeah, that was way easier, okay? Now, of course, it's not always way easier. Like not everything is easier in parametric, but it's important to know that sometimes it is and sometimes it's not. So we need to develop that skill in terms of being able to use this formula. Okay.
So to confirm the slope on this, we just take our t equals 2 and we use it in the y of t equation?
Yeah.
And then, okay.
Yeah.
Oh yeah, where the y is.
Exactly. Because if this, so this is a y, that's why I'm only plugging it into the y equation. But if I found my dy dx and I had x's in there also, I'd have to take that 2 and plug it into the x equation as well to find the corresponding point.
Cool.
Okay.
Sounds good.
All right. So last but not least, let's practice writing the equation of the tangent line at t equals 2. Okay. So when we're looking at the equation of a tangent line, everything is with our x's and y's. So it's the same deal. It's the y minus y1 equals mx minus x1. Okay. And so we need to know our slope, which we do. We already have our slope of 1/2. And then we need to figure out what point xy corresponds to t equals 2. And so we already know that when we plug in 2 into the equation for y, we get 3. So I can go ahead and put a minus 3 in for the y. Okay. And Sean, you asked a great question. Couldn't have asked for better timing, because now I'm going to take that 2, I'm going to plug it into the x equation so that I have something to fill in for the x1. So 2 squared is 4. 4 minus 3 gives me 1. And so the point that corresponds to t equals 2 is 1, 3. So that I can fill into my equation. Okay. And then I love that folks are getting used to leaving it like this. And then the nice thing about leaving it like this is the only thing we need to change for the normal line is to make it a negative reciprocal. Okay. And you don't have to write as 2/1. You could write it as 2. That would be absolutely fine. All right. Any questions on example 1? All right. So let's finish off this example by graphing the equation and sketching the tangent line and the normal line, okay? If you haven't noticed by now, I really like pictures to go with what we're doing. And I actually feel like a lot of us out there are very visual learners. And sometimes when we get into the higher math, we're like, I don't know, I'm just doing all this algebra. Like, what does it even mean? But when we can put it back on a diagram, it just makes it a little bit more clear, okay? So I'm gonna start by sketching my XY axis. X, Y. Okay. And our graph was a parabola facing sideways. Yeah. And so if we sketch that parabola, we should end up with something kind of like a I think that it's actually moved up 1 unit, but we're really just kind of sketching like what that is. If you want a more accurate diagram, you can definitely put it into Desmos, and you could plug in the rectangular form that we had right here. Okay. But if we're thinking about tangent lines, okay, we knew that the point we were interested in is 1, 3. So if I go to 1, 3 on my curve and I draw the tangent line, it's gonna follow the slope of that line, but it's just gonna touch the curve right at that one spot, okay? So this one would be the tangent line. And then if we wanted to visualize the normal line, it's just gonna be perpendicular to that. But they go through the same point. And that's why we can keep the 1, 3, because it's the same for my actual curve, my tangent line, and my normal Okay. All right, now I think we're ready to move on to example 2. All right, so example 2, we're given parametric equations x equals t cubed minus 3t and y equals t squared minus 5t minus 1, and we're looking over all real numbers, okay? And so in a case when we're looking at all real numbers, the smallest, or your quote unquote starting point, would actually be at negative infinity. So you're plugging that negative infinity first and seeing like, where is my curve starting? And then the last point that you plot is your infinity, right? So you plug in infinity for x and y and kind of see where the graph ends up. Now, if you're not sure about the direction, it might be helpful to try a couple points in between, like 0 is always a nice number to plug in. 1 might be a nice number to plug in just because they're easy to compute. And that might help you give a little bit more sense of the direction in which your curve is going. All right, so this question here has 3 parts. It says, write the equation of the tangent line at t equals 2. Then it asks, where is the tangent line horizontal and where is the tangent line vertical? Okay. So let's start off with the equation of the tangent line at t equals 2. And we're going to use the dy dx equals dy dt over dx dt to help us find the slope. Okay. So dy dx equals dy dt over dx dt. Now, you don't have to write this out every time, but I didn't leave a space for the formula per se, so I just wanted us to get a chance to see that formula as we work through the problems that it applies to. Okay, so let's take our derivative of the numerator. That's going to give us 2t minus 5. And what do we get when we take the derivative of the x?
3t squared.
Yeah, 3t squared
Minus 3.
minus 3. Perfect. All right. So we've got 3t squared minus 3 in the denominator. All right. So that would be like, in general, that's my dy dx. Now I'm going to plug in 2 for t, so I get the slope at the point that I'm interested in. And that's going to give me 4 minus 5 over 4 times 3 is 12 minus 3, or I will get negative 1/9. And that's going to be my slope for my tangent line, okay? So I get y minus something equals negative 1/9 x minus something. And so I'll give you a moment to find your x and your y value that correspond to t equals 2, and then let's fill them in, okay? All right, anyone get a value for x yet? X1.
2.
2, yeah, that's what I got. And then for the y1?
-7.
Yeah, I got -7 as well. Okay, and so we could definitely clean this up just by distributing that sign. So we get y plus 7 equals negative 1/9 x minus 2. And there we have the equation of our tangent line, okay? So that's one useful thing for knowing the slope of a set of parametric equations. So what does it mean when we're looking at a tangent line that is horizontal? What does that mean, like visually or conceptually?
When the slope is 0?
where the slope is 0. Good. So this phrase, tangent line is horizontal, really means where the slope equals 0. Okay? In other words, where does dy dx equal 0? Okay? Now that's what it means conceptually. Calculation-wise, dy dx is a fraction. The only way that I can get 0 out of a fraction is if my numerator equals 0. Okay? So dy dx equals 0 implies that dy dt equals 0. I don't even have to worry about dx dt, because if I have a 0 in the numerator, 0 over anything is going to give me 0. So I'm just going to take the denominator, or the numerator, 2t minus 5, and I'm going to set that equal to 0. And whatever t value makes that true, that's where the tangent line is going to be horizontal. So in this case, t equals 5/2 is where that tangent line is going to be horizontal. Okay? So great question here about what if dx is 0, and so that's what we're going to explore in the next case. Okay, so that is sort of the exception to this tangent line situation being horizontal. So you want to make sure that when the t value makes the numerator 0, that means the slope is going to be 0. Okay, but when we're looking for a tangent line being vertical, we're really looking for the slope to be undefined, okay? Now, if the slope is undefined, that means that dy dx is undefined. And that implies that dx dt equals 0, okay? So when the denominator, the dx dt part, when that equals 0, you're going to have a dy dx that is undefined, which is the same thing as saying that the tangent line there is vertical, okay? So let's take our denominator. We're going to set it equal to 0. Now, you could solve this one of two ways. I tend to go for factoring, okay? Because with factoring, we tend not to lose answers. So what I mean by that is I would factor out a 3, then I'm left with t squared minus 1, which I can factor into t plus 1 and t minus 1, and that would be what I want to equal 0. That means that the two values that make that have a tangent line that is vertical is t equals positive 1 and t equals negative 1.
So I just have a question about that, Professor.
Okay.
So does that mean that at time 1 or time minus 1, that's when we will get that?
Yes. Yeah.
Okay.
Okay.
Thank you.
All right. Now, I just want to show the alternate way to solving this equation, which some of you may have already done. I bet some of you moved the 3 to the other side and then divided by 3 and then wrote your answer. And then as soon as I was like, oh, there's 2 answers, plus or minus, you're like, oh, right, plus or minus. And then kind of like squeeze that right in there, okay? There's nothing wrong with doing the method in blue, but most of the time when students forget one of the solutions, it's because they did the way in the blue. And they're working so quickly on a test or whatever, their homework, and they get to it and they're like, yeah, t equals 1. And for some reason, that method, folks generally forget the plus or minus, okay? If you happen to be the exception to that rule and you're like, no, I remember the plus minus every time, then sure, go for it, okay? But if you're like, yeah, I do forget the plus minus, then maybe think about building up that factoring a little bit so that you won't forget that plus or minus, okay? But the key takeaways from this problem are that we know when the slope is 0, that we have a horizontal tangent line, and that means that dy dt equals 0. But when we have a slope that is undefined, that means that the tangent line is vertical, and we can find that location by doing dx dt equals 0, okay? So horizontal means slope is 0, which means dy dt is 0. And tangent line is vertical means the slope is undefined, and we can find that by setting dx dt equal to 0, okay? All right. I think I'm trying to get over my like don't use too much paper thing. Sometimes I don't leave myself enough space, but hopefully this will be enough. All right, so example 3, given the parametric equations x equals 2 cosine 3t minus 4 sine 3t and y equals 3 tangent 6t, okay? Write the equation of the tangent line at t equals pi over 2. So I wanted us to do an equation with trig in it because I feel like sometimes that unit circle just needs a little bit more refreshing, and we really want to make sure we know these values, okay? And we've been working so much with integrals that it's also important to remember which answer gives us the integral and which one was actually the derivative, okay? So if I want to find the equation of the tangent line, I know that I need to find the slope. And so let's set up finding our slope here. dy dx is going to equal dy dt over dx dt. And so I'll give you a moment to find the derivative of dy dt and dx dt. All right, so when we take the derivative of 3 tangent 6t, we should get 3 secant squared of 6t. But if we stop there, we would be incorrect. We would be missing a factor of 6, okay? Where did that 6 come from?
Chain rule.
Yeah, it comes from the chain rule, okay? So a lot of times when we like start to apply derivatives and integrals to other applications, like rather than just doing them to do them, we end up with integrals or derivatives that are actually not that bad, but it's little things like the chain rule or the u sub that we end up with something that's off by a factor of something, okay? So I'm glad that we were quick to recognize that we have the chain rule here. And then if we take the derivative of the x, same thing, we're going to need chain rule for both parts. And so the derivative of 2 cosine 3t is going to be negative 2 sine of 3t times 3. That takes care of the chain rule for the first part. And then minus 4 cosine 3t times 3, and that would take care of the chain rule for the second part. Now, some of you were probably able to jump right to the actual derivative, which is fine, okay? But we've got 18 secant squared 6t, negative 6 sine of 3t, minus 12, minus 12 cosine of 3t. And since I know I'm going to be plugging in some numbers, I look for any factors that I could divide out, and I notice that I can divide all 3 terms by 6. So I'm going to write this as 3 secant squared 6t over negative sine of 3t minus 2 cosine of 3t. Okay. Now this step is optional. You don't have to do that. If you have a calculator, it probably doesn't matter. But sometimes it just is nice to get in that habit of looking to reduce things. And so the value I'm going to plug in now is pi over 2. So let's see what happens when we plug in pi over 2. We will get 3 secant squared of 6 times pi over 2 is 3 pi. Okay. And then on the bottom, I have negative sine of 3 pi over 2 minus 2 cosine of 3 pi over 2. So we've got some nice unit circle values here. And the secant of 3 pi is actually negative 1. And I'm going to have to square that because it's secant squared. And then my sine of 3 pi over 2 is negative 1. So I have negative 1 minus 2 times cosine of 3 pi over 2 is 0. So I end up with 3 over 1, or a slope of 3. All right. So to finish this problem, we need to plug this into our point slope form. So I can already fill in this 3, and I have my x and y. Now I need to find my x1 and my y1, okay? So to find my x1, I'm going to plug pi over 2 into the equation for the x, and I get negative 4, so a positive 4. And when I plug pi over 2 into the y equation, I get 3 tangent of 3 pi, which is going to give me 0. Where are you getting negative 3 from? Two times 0. Right, so the 2 times 0, that term goes away. Yeah, order of operations, okay? And sometimes to prevent myself, I even just like, if I know it's multiplying to 0, I'll draw that, or I'll write that out on my work so that I don't make that similar mistake, okay? All right, So this seems like a good place to pause, okay? We have one more type of work with slope that we're gonna do when we come back. We're gonna look at not just the first derivative, but we're gonna practice finding the second derivative. And then we're gonna jump into integrals, okay? So we're gonna do a little bit more with derivatives, but the most of the second half of class will be on integrals. So we're going to switch our brains to go not just from taking derivatives, but switch it back to taking integrals. Okay, so it is 10:16 right now. Let's be back at 10:25. All right, folks. So
Professor,
yes.
I have a quick question about quiz number 8. Will you have time to answer that after class?
I don't know. It kind of depends on how far we get.
Okay, thank you.
Okay. All right, so I'm going to go back and share my screen so we can take a look at what second derivatives look like in parametric equations. All right, so second derivatives. Now here's the deal with second derivatives. I actually want to start with the thing outside of this blue box because that is not what the second derivative is, okay? So lots of times we think, well, if I take the first derivative, if the first derivative is dy dx or dy dt over dx dt, then the second derivative must mean that I just take the second derivative of the top and the second derivative of the bottom. And I just want to point out right here, this is not, well, this is not what the second derivative of parametric functions is, okay? Instead, what we need to do to find our second derivative is we need to take our first derivative and take another derivative. That's why we have this d dx of my first derivative. So this is saying find derivative of the first derivative. That gives me the second derivative. And in order to do that, I need to take my first derivative, okay? So find the derivative of dy dx. So you find your first derivative, you find it again, and then you put that over your first derivative for x of t. Okay, so whatever that derivative was, you're going to go ahead and keep that on the bottom, and on the top, that's where you're going to take the derivative of the whole first derivative.
Can I ask something?
Yeah, what's up?
So basically what you're saying is you're going to go ahead, you're going to do like a little Hopital's kind of thing going on where you take the derivative of the top, derivative of the bottom, and then it's going to turn into like a chain rule, or no, a quotient rule.
No, what I'm saying is we are not doing L'Hopital's. L'Hopital's would be like the red box, right? Where we just take the derivative of the top and the bottom and keep going. So do not do that. But let's see this in practice, and maybe that might answer some of those questions, okay?
Okay.
Okay. Okay, so given the parametric equations here, let's take a look at finding the first derivative. Okay, so that part is something that hopefully we feel comfortable with. So if I'm finding the first derivative here, I know that dy dx equals dy dt over dx dt. And when I find my dy dt, I'm going to get 2e to the 2t, right? Because I have to use the chain rule for that y component. And then for the x, I'm going to get negative e to the negative t. because again, I'm using chain rule. Now, when I simplify this, okay, when I simplify this, I'm going to get a negative 2, because 2 divided by that negative on the bottom gives me negative 2. And then e to what power?
3t.
E to the 3t. So we just add that exponent, right? 2t minus negative t gives me 3t. So I found my dy dx, okay? That's what we did before. But in part B, it says find the second derivative, okay? So what we want to do is we're gonna take our dy dx, okay? And the derivative of this is going to be this numerator up here. And then in the denominator is going to be whatever I had in the denominator before I simplified, that negative e to the negative t. So let me write out the formula. All right, so to find the second derivative, we're going to need to find the derivative of the first derivative. And then we're going to divide that by the first derivative of x. So that's going to give us negative 6 e to the 3t, because that's my chain rule right there to find that. And then divided by my original derivative for x, which is negative e to the negative t. Okay. So before we simplify, let's just take a look at this whole screen and make sure we know like where things came from and where things went. James, does that clarify your questions or no?
Yeah, the way that I was thinking about it, like I understand exactly the process that you're doing it, but what I was thought that you were going to do is you were going to take the derivative of the top and the derivative of the bottom, and then when you get to the part where you simplified, if you still had a fraction, then you would use that quotient rule. Whatever comes out of there goes on the top, and then your denominator goes on the bottom.
I see. Yeah, so we're not doing that, right? So we do want to just have that derivative of the top, but this piece right here, like the dx dt that you use in the first derivative, whatever comes out, that's the same dx dt that you use down here.
Yeah, I totally see that.
Okay.
I'm just like, because this one worked out because you were able to simplify it to like one plane, whereas like I'm pretty sure that when it comes to quiz time and test time, we're going to get a fraction that we're going to have to use the quotient rule with.
Yes, yes. So that, let's leave a little note for ourselves, because I do believe in some of the quiz questions that it doesn't necessarily reduce to a non-fraction, okay? So if dy dx is a fraction after simplifying, then you will need quotient rule to take that derivative, okay? So if you end up with a fraction where I have that negative 2 e to the 3t, then you're going to have to use quotient rule. So it's just whatever you can simplify it to. If there's a product involved, you would have to use product rule. If there's a quotient involved, you would have to use quotient rule. So whatever rules that you learned before still apply, but you only use those to find the new numerator, and you put it over the same denominator you had in the first derivative. Okay.
Thank you for helping me clarify.
Of course. I think a lot of folks tend to have that question. So. All right, so if we simplified this one, that negative 6 and the negative 1 reduced to a 6, and then this gets e to the 3t minus negative t, or 4t. All right, So second derivative, first derivative. All right. Do be really careful on the second derivative questions, because I think the first derivative ones aren't bad, but it'll take a little while to kind of get the hang of the second derivative. I do think it's just a little bit trickier, and you're like, am I putting this in the right place? So come back to this example and definitely use that as you're going through that. Okay, so we are going to move on to integrals and how integrals can be applied for parametric equations, okay? So the application that we're going to take a look at here is something called arc length. Now, if you were in 150 with me, we actually didn't get to arc length because we lost that week in the spring due to going surprise remote learning. But if you were in other classes, hopefully you did see arc length before, okay? But either way, what arc length is if I think back to my starting picture, let's actually go back up to that parabola. Okay, so when we had this parabola, we were thinking, let's just graph it, and then we were thinking, let's find the slope. But when we're thinking about arc length, what we're really saying is, let's find out how long a certain piece of the curve is. So for example, I could figure out exactly how long it is from that pink dot to the green dot. That's what we call arc length, okay? And arc length has a special formula for it, which we kind of saw down at the bottom, okay? Okay, so what we know, again, probably isn't true for folks who were in my section of 150, but hopefully is true for those of you who had other 150 instructors. But arc length, we often denote with the letter L, L for length, okay? And if we're looking at rectangular functions, then we could use this formula. The integral from a to b of the square root of 1 plus dy dx squared, and then a dx on the outside. That would be if you wanted to find it with respect to x, but you could certainly flip it so that you were changing your perspective. Sometimes it's easier to find with respect to y, all right? So the integral from c to d of the square root of 1 plus dx dy squared over, or times dy, okay? Now the format of this maybe is a little bit more clear in when we look at the parametric one actually, because this formula actually comes from the idea of the Pythagorean theorem. So if we think about the Pythagorean theorem, we've got a squared plus b squared equals c squared, right? We all know that. And we also know on a diagram that the a and the b represent the horizontal and vertical components, but the c always represents the hypotenuse, okay? So the short version of where this arc length formula comes from is, once upon a time, someone was like, well, here is this curve, okay? And if I want to find out how long a curve is, what I can do is cut it up into tiny, tiny segments. The tinier, the better. And each segment, so let's say I said like this segment right there, I was going to plot it kind of as like the hypotenuse of a tiny triangle. Oof, when I zoom in, it doesn't look so good, but we'll go with this. And then if I wanted to find the length of another part of it, I could say, well, this part is the hypotenuse of another baby triangle. And I could have a lot of baby triangles, in fact. So maybe I have another one over here, which gives me this part, okay? And I won't continue to do these not so great diagrams, but I think you get the picture here, is that we could take a long curve, we could cut it up into tiny, tiny sections, and every section would be like the hypotenuse of a right triangle. And so if we cut it up into an infinite number of tiny triangles, and we find all those hypotenuse, whatever the multiple is of hypotenuse, if we find all of those lengths and then we add them all together, we're going to get the length of the curve. Okay? Now, if I make the triangles really tiny, what happens is that every hypotenuse actually matches perfectly with that small piece of the curve. And so we can use the idea of distance for linear functions even when it involves a curve like this, okay? So where does all that notation fit in the formula? Well, the dt at the end really means I want tiny, tiny, tiny triangle, okay? This part right here is really saying c equals the square root of a squared plus b squared. Okay, so that square root symbol is there because otherwise I would be finding the hypotenuse squared, but I just want to find the hypotenuse. And then the last piece of notation, this integral symbol, we know it as an integral symbol, but what that really means is after you cut the curve into tiny, tiny pieces, you need to add them all together. And it even tells you where to start adding and where to stop adding. Okay?
So the meat and the potatoes of the equation is the hypotenuse?
Yeah. Yeah.
Okay.
That's really just finding the hypotenuse. Okay?
Got it.
Mm-hmm. This integral symbol, one way that we're going to start to see the integral symbol is that for adding up a bunch of things, sometimes we use sigma or the summation, ooh, that's not attractive, or the summation symbol, okay? And so it's the same kind of thing where we're saying, let's add up a whole bunch of things. All right, so that's a little sort of background on arc length. But let's think about how it's used in the context of parametric equation, okay? Now there's one small thing I want us to make sure that we know this does not include. So yesterday, when we started looking at plane curves, we had like sort of like this curve that kind of went like that. Like that's totally fine. We can use the arc length formula for this curve. There was one where it was kind of like this blobby looking thing. We said it was like a simple closed curve. We could use it for a simple closed curve. But when we're looking at like, there was one where it kind of like looped itself twice, okay? The arc length formula has certain restrictions. We aren't going to use this arc length formula when the curve does not cross itself. Okay, because what we're assuming is that we're starting somewhere and we're stopping somewhere where we can calculate from left to right. And that becomes problematic when we're looking at like loops, because which part of the loop are we looking at? But it's also kind of problematic when we're looking at some of the simple closed curves. So we're really focusing on a situation where the curve does not intersect itself, okay? All right, so let's see what some of these look like. All right, so when we're looking for this intersecting itself, okay, we really want to, oh, shoot, I didn't mean that one. We really want to think not like crossing itself multiple times, okay? So let's start with something that is fairly visual for us, okay? So example 5 says, find the arc length of the parametric curve given by x equals 3 sine t and y equals 3 cosine t one time around the unit circle, 0 to 2 pi. Based on yesterday's, we know this is going to give us a circle. And how do I know it's not an ellipse?
Because the coefficients are the same.
Yeah, because the coefficients are the same, exactly. So we know it's a circle, and we even know the radius of that circle, 3. So let's zip back in time, maybe to like when Pi Day was fun for you. And you first learned about circles, and someone said, all right, well, for a circle, here's a circle, and you have the radius of 3. And if somebody said, I'd like you to find the circumference of the circle, what they were asking you to find is equivalent to our more grown-up term of arc length, right? They were asking you to find how long around is this circle? So the arc length, we could actually answer this question just by using the circumference formula if we can recognize that it's a circle, okay? So that's one of the benefits to being able to recognize the shape. Sometimes you can shortcut things without having to do a lot of the other calculus, okay? So circumference formula we have as 2 pi r. And when we plug in our radius, in this case, it's going to give us 6 pi. So I know that the arc length that I'm going to find in method 2 should give me 6 pi. Okay? No. Sorry, we've got a frozen situation here. Okay, sorry about that. So let's use this idea of something that we know to confirm our answer using this fancy and maybe intimidating looking formula, right? Show ourselves that we can get to the same answer, and then it'll be extra confirmation that we are correct in the calculus work. So I'm going to set up my equation, okay? My arc length is going to equal the integral from 0 to 2 pi, because that's where I start and that's where I stop. The square root, okay, so this is like the square root of a squared plus b squared. So I need to find the derivative of x, and I'm going to square it. And then I'm going to add it to the derivative of y, and I'm going to square it. And I want to make sure that I have a dt at the end. So the derivative of x is going to be 3 cosine t. And the derivative of y is going to be negative 3 sine t. Okay. So before we continue working this out, are there any questions about the substitutions that we made from this formula to our question? Okay. So let's simplify now. So if we simplify, we end up with the integral from 0 to 2 pi of 9 cosine squared t plus 9 sine squared t dt, which is pretty wonderful because I notice that both terms have a 9, so I can factor that out. And I know that the square root of 9 is 3, so I can even bring that 3 all the way to the front. What's left under the square root is cosine squared t plus sine squared t. And if we remember our Pythagorean identities, another way to say cosine squared plus sine squared t is 1. Okay, very handy substitution. So really, what we have is we have 3, the integral from 0 to 2 pi of 1 dt. And when we take that integral, we end up with 3t, and we're going to plug in 2 pi, and we're going to plug in 0. And that's going to give us 6 pi minus 0, or 6 pi. Okay? So we're able to confirm our answer, something that we knew for many, many years. Here's the circumference formula for a circle. And now we're able to look at it if we had a parametric equation. So a different way of naming that curve, we're still able to manipulate it in this formula so that we get that arc length, okay? Any questions on example 5? Okay. All right. So we've got one last question here, okay, which is example 6. And example 6 says this: find the length of one arch of a cycloid, which is given by the parametric equations x equals t minus sine t and y equals 1 minus cosine t. So as you get into higher math, one of the neat things is you'll see all these sort of special kinds of shapes, and the cycloid is one of those, okay? So the cycloid, if I were to draw like a full graph of the cycloid, what I would end up with is something that looks like a bunch of arches, okay? But here's how these arches happen. A cycloid is just, you have a circle, you have a certain point on that circle. So like, so say this point right here. And as the circle rolls along the x-axis, the graph that is generated is where is that blue dot at any point in time. And so what happens is you end up with a situation where it's like this, and then it keeps going, and then it keeps going, okay? So kind of like a trig function, there are a lot of different waves for a cycloid. It just kind of keeps going. So when I say t is an element of real numbers, that means that I could these arches go back and forth in both directions, okay? The circle just continues to roll forever and ever. And so in this particular question, we're trying to find the length of just one arch, okay? So what happens is when we have this circle rolling on the x-axis, okay, the distance from when it started to when it stopped, it starts at one location on the unit circle or a circle, and it finishes after one rotation, so 0 to 2 pi, okay? I believe in the quiz, you have a question about an asteroid, so it's kind of similar to a cycloid in that you take a circle and you like move it around the graph a little bit and you get a cool looking graph, okay? But the one arch for the cycloid goes from 0 to 2 pi. And so let's go ahead and set up our equation to find the arc length of one arch. So our bottom bound is going to be 0, and our top bound is going to be 2 pi. And then we have our square root, and we're going to need to find the derivative of x, and we need to square it. And then we need to find the derivative of y, and we need to square it. So the derivative of x gives me 1 minus cosine t, and I'm going to square that. And I'm already making a mental note, better FOIL this, don't just distribute that square, okay? And then to that, I'm going to add the derivative of y squared, which will give me sine t squared, okay? So let's start expanding. This is going to give us the integral from 0 to 2 pi of 1 minus 2 cosine t plus cosine squared t plus sine squared t dt. And kind of like before, this part goes to 1. So underneath this square root, I really have 2 minus 2 cosine t. All right. We're going to go ahead and factor out that 2, and we're going to remove it from our square root. So that's going to give us,
where'd the 2 come from?
1 plus 1.
Okay, I see it.
You see it? Like this one plus this one.
Yeah, yeah.
Yeah. All right, so we've got the square root of 2 that I'm going to pull as a constant all the way out to the front of my integral. Okay, so square root of 2, the integral from 0 to 2 pi. And then underneath the square root, what I have left is 1 minus cosine t. Okay. Now, we're going to take a little bit of a sort of sidestep here, okay? And we're going to think back to some of the other identities that we know. So we have a power reducing identity that says that sine squared of theta equals 1 minus cosine 2 theta over 2. Okay, so we tended to see like the cosine squared. We've been subbing that out with the 1 plus cosine 2 theta over 2. All right, so the sine squared substitution is similar, except it's 1 minus that cosine 2 theta. And so I'm going to multiply the 2 to the other side. So I'm going to get 2 sine squared theta equals 1 minus cosine 2 theta. Okay. And then I'm getting closer to what this looks like, except I don't have a 2t, I only have 1t. So how does that play out here? Well, this identity can also be written as 1 minus cosine theta. But if I change the 2 theta to a theta, what does this change into?
Over 2.
Yeah, I'm cutting it in half. So I have sine squared of theta over 2. Okay. So let me pause here for a moment. Make sure that we all understand that reasoning there about why we can just cut the angles in half, okay? So the bottom line is that this identity is going to be true as long as the relationships between the theta and the 2 theta hold true. So this theta, if I double it, I get the 2 theta. Does that hold true for our assumption? Theta over 2, if I double it, I get 1 theta. And it does, okay? So we can work the trig identities like that, where if somewhere it says a 2 theta and you want to change it to a theta, then you cut all the other thetas in half. But what that allows us to do in our integral is replace 1 minus cosine t with 2 sine squared t over 2. Okay, so I took this and I substituted it in for the 1 minus cosine theta. Now I'm going to be able to take the square root. So I take the square root of the 2, so I get another square root of 2. So square root of 2 and a square root of 2 are my new constant. I have my integral symbol from 0 to 2 pi, and the square root of sine squared is just sine. All right, root 2 times root 2 gives me 2. What is the integral of sine t over 2?
-2 cosine t over 2?
Yeah, -2, because of the u sub, cosine of t over 2. Good. And I'm going to plug in 2 pi, and I'm going to plug in 0. Sorry, I don't know why there's a lag today. It was definitely bad. I'm going to distribute that 2, so I get -4 cosine t over 2, plugging in 2 pi, plugging in 0. And I get -4 times cosine of pi minus cosine of 0, which gives me cosine of pi is -1, minus cosine of 0 is 1. And so I get -4 times -2, which gives me a positive 8. Okay. So that means that when this circle rolls along the x-axis, every time it rolls one rotation, it's going to travel a distance of 8. Like that dot travels a distance of 8 units. Okay. Now you'll know that something goes wrong if you get like a negative number, because we're talking about arc length. So we want to make sure that we're getting positive values here. Okay. And that can be a little tricky when we're working with cosine and with negative values. So just make sure you plug in the right values there and that everything works out.
So we plug in pi instead of 2 pi?
Well, 2 pi divided by 2 gives you pi.
Oh, yeah, okay.
Yeah. So we did plug in 2 pi, but it divided by 2, so we got pi.
Oh, yeah, that's right.
Yeah. I know, this is the simple math that gets you, right? Yeah.
Yes.
Yeah, you're right, Jorge. Okay, so that is it for today in terms of parametric equations. Yesterday we did sort of a foundational knowledge, so a review of what you covered in pre-calc. And then today we focused on applications to calculus. So we looked at slope, tangent lines, horizontal and vertical ones, second derivatives, and then we shifted gears and we talked about arc length, okay? So that is it in terms of today's lesson. So I'm going to stop the video here.